All right, so let's talk about convection and radiation resistances. I told you could do the same thing. So let's get through at least the convection part. We'll see how far we get. All right, so let's go back to the convection rate equation, Newton's law of cooling, and that is Q dot equals H bar AS TH minus TC. I want to write it in terms of the same potential that we've been thinking about. So here we have H bar AS, then the hot and cold potential. So maybe just looking at this, you can kind of see what the resistance formula is for convection. Right, it's some constants, HAS times a potential. So our convection is the inverse of what's multiplying that stuff. It's just 1 over H bar times AS. So that one's easy, right? That's straightforward. Let's talk about radiation. Sorry, so this is radiation here. So let me write the radiation equation. We have Q dot radiation is equal to sigma times epsilon times AS times T, let's call it TH to the fourth minus TC to the fourth. So this one is sort of the same, but very different. Instead of this potential, like high voltage to low voltage, high temperature to low temperature, now we have the potential to the fourth. So that's a problem, right? The resistance model kind of breaks down if you have this quartic term in there. So we have to think about how we can maybe express this in the same way. If we want to use a radiation resistance model, we have to express in terms of just a potential, like a straight, one temperature minus the other. So there's some kind of weird steps that we can go through to get to that. I'll do that kind of quickly, maybe the last thing we do here. All right, so let's take this. So let's take this here, this term, and recognize that you can break this into two terms that multiply each other. So TH squared plus TC squared times TH squared minus TC squared. Okay? So we're trying to break this thing up. It's equivalent, right? We're just breaking it up into two terms multiplying each other. So we're closer. Now we have this potential TH minus TC, but they're squared. So maybe we can break that one up a little bit further. So let's break this one up. And how does that look? So we end up with, again, TH squared plus TC squared times TH plus TC times TH minus TC. All right, so let me rewrite this all out here. So I'm going to say Q dot radiation is equal to, let's move this over. Q dot radiation is equal to sigma epsilon AS times that whole thing. So if you're like kind of anal about stuff, the next step is really going to be annoying for you. But basically what we do is we take this whole mess here and we call this the resistance. All right? So this is 1 over R radiation. So technically we have stuff multiplying a potential and we're good, right? I mean, the obvious complication is that TH and TC are part of the potential. And so it's not quite right. It's an approximation. But it turns out for most cases it's actually okay, right? As long as you have like temperatures are, roughly the knowledge, you can kind of put a guess in there and then compute the resistance that way. All right, so we'll come back to that a little bit. I think, yeah, I'll come back to that next time. Thanks, everyone.